Death sucks, and I think that when we have been socialized to accept death.
Immortality is defined as the ability to live forever or to have eternal life. On the other hand, another type of immortality, called biological immortality, is the act of never aging. Although you can still die from another of things besides age-related deaths, biological immortality is still an extremely difficult code to crack. Senescence is something all living organisms have, which is a gradual deterioration of normal functioning, also known as aging. Although every organism has senescence, some organisms have found special tricks to get around it, by cracking the code to biological immortality. A jellyfish species is able to grow old into an adult stage to reproduce, then can turn back its life cycle, reverting back to its first stages as a polyp. This jellyfish can continuously do this all its life, gaining biological immortality. So, why do we even age in the first place? There are many theories to this question, most stating how DNA is damaged over time.
That we're not going to get rid of death. It will eventually catch up with us, death and taxes. And I think it is part of...
The most agreed upon theories seem to include a top 3 reasons of why we age: telomere shortening, oxidative stress, and glycation. Oxidative stress includes free radicals and occurs when there is an imbalance between these free radicals and antioxidants. Free radicals are oxygen molecules containing one or more unpaired electrons and are highly reactive because of this. These oxygen molecules can interact with important macromolecules, such as nucleic acids, which make up our DNA. They react by stealing electrons from other molecules, destabilizing these molecules. That's where antioxidants help. They donate electrons to free radicals without destabilizing themselves. An influx of dangerous free radicals can lead to Parkinson's, Alzheimer's, cancers, heart failure, and many more dangerous diseases. Glycation is where sugar and protein molecules in our body combine, forming a tangled mess of tissue. This tangled tissue is tough and inflexible, often producing lots of free radicals in the process. Because many of our organs, such as our heart, kidneys, brain, and eyes, rely on flexible tissues, glycation can be devastating and has been found to lead to earlier death.
Triglycerides have different rates of promoting glycation. Glucose is more stable, and its stability and reduced...
And then there's telomere shortening, the most talked about subject when it comes to discussion with immortality and aging. Telomere shortening is a completely normal process and can only be understood by going through a detailed walkthrough of DNA replication.
To make perfect copies of our DNA, an enzyme first unwinds the 2 strands of the molecule by separating its base pairs. Another enzyme then attaches free nucleotides to the exposed sites. The existing strand determines the composition of the new strand. According to the base pairing rules, adenine bonds with thymine and guanine with cytosine. In long strands of DNA, replication occurs in many regions simultaneously, forming the sister chromatids.
Although much more simplified, the video showed you how DNA is replicated. Unzipped, copied, and you're done. But where do telomeres come into play? When DNA is unzipped, there are 2 lone strands of DNA, one a leading and one a lagging. DNA is anti-parallel, which means that instead of both pieces of DNA being parallel and going the same direction, one strand goes one way, another goes the opposite. Leading and lagging strands just refer to which direction that single strand of DNA is going in. Here's where it gets even more complicated though. DNA can only be copied in one direction, so while the DNA is being unzipped, one strand of DNA can be copied, going towards the unzipping, while the other strand has to be copied going away from the unzipping. The reason telomeres are needed at all is because of the leading strand. DNA is replicated away from the unzipping of DNA, leading to fragments later sealed up. This sealing of the DNA is important. Whichever direction the DNA is being copied can get sealed off at the end. However, wherever DNA begins to be copied cannot be protected, leading to a possible damage in DNA. This possibility of damage is protected by telomeres, sacrificing themselves a little at a time so actual DNA is not harmed. To be more concise, when DNA is replicated, some of it runs the risk of being destroyed. To protect that precious DNA, telomeres are instead put in. However, telomeres don't last forever, and they can shorten down, causing devastating effects on DNA. The main reason telomeres are a big theory on why we age is because once they're gone, cells can no longer replicate correctly, leading to many age-related diseases. And think about it. If telomeres were indefinite, cells would never have to stop dividing, which can lead to biological immortality many scientists seek.